100 times finer than cement grains. What it is, he's asleep, I was going to throw it to him, but here you go. That's actually silica fume. That's a full container of silica fume. If you think of the word silica fume, fume in Latin means, anybody? Close. No fumada. In a restaurant bathroom, no fumada. No smoke. Fume is smoke in Latin, or French, Italian. And it actually is silica smoke. That's captured smoke. You can open up the container and look at it, it's fine. It won't jump out, it won't float away. You throw it in the air, half of it will probably stay in the air, but the material as it's captured, this smoke weighs about 8 pounds a cubic foot. Water weighs 62.4. This weighs 8. It's captured smoke, literally. The plants used to look like this. Obviously this is taken out of the user's manual that you have in front of you. Should probably say something about the user's manual first. That's written for producers and practitioners of concrete. It's written for ready-mix producers. It's written for contractors. It's not an engineering document. It's a real how-to. The first couple chapters deal with the background, like this is actually in chapter 1. What is silica fume? Where it comes from? All those things that we're going to cover here real quickly. Latter parts of the book, chapter 6 deals with mix designs and proportioning. Chapter 8 deals with contractor issues of placing and finishing. So it's all written, the FHWA wanted a document. We have enough engineering documents on high performance concrete. We needed something to take from that industry back to the people that actually have to build with it and teach those people how to build with high performance concrete. That's what this manual is dedicated to. I think it's perfect for what you guys are headed for.
If you put 1 spoon of this material in a cup of water, what will happen?
You'll have dirty water. You can actually mix it in with water. The one video that we'll see on the dam that's being repaired, the way of introducing that into the concrete was actually in a liquid form where they suspended the silica fume in 50-50 in liquid versus trying to handle it in a dry form. That was before they figured out how to handle a material that light in a dry form. What they found was, and I thought this was pretty unique too, they put that material in a big silo about 6 stories high and blow a lot of air, very low pressure, but about 700 CFM of air through the bottom of this silo. If you stand at the top of the silo and look down on the top of it, it looks like the whole thing's boiling. It's just all kind of air coming up through the silo. What happens is when the air goes through this column of silica fume, it causes those little particles to collide. And because of van der Waals forces, the attractions of fine particles, they actually start sticking together. And so we can actually increase the bulk density of the silica fume from 8 pounds a cubic foot up to about 40. And once it gets up to 40, then they can haul it around and put it in trucks and blow it into silos and treat it like cement and fly ash and treat it like any other material and handle it. Can't handle it when it's 8 pounds a cubic foot. When you get up to about 40, you can handle it with that way. But I think it's strange because normally, if even like flour or something, if you want to fluff it and make it lighter, you blow air in it. Right? And it fluffs everything back up again, just like shaking that up in a container, you'd fluff it all up again. But if you do that long enough, if you fluff it long enough, it starts getting heavier, which I think is a neat trick. But anyhow, this is a schematic of the plant that produces silica fume. What they're doing at point A is they're putting in quartz, big rocks about the size of your fist, almost pure white. Quartz, coal, wood chips, and coke, and ignite it all in an open arc electric furnace. The electrodes anywhere from 24 to 30 megawatt electrodes. You walk into the furnace building, I swear you can feel the straight electrical current in the air. It's so powerful. But what they're doing is they're melting the quartz. And they're melting the quartz to extract silicon. Element number 14 on the periodic chart, Si. That's a chunk of it here that we'll pass around. The only thing you make out of silicon is silicones. Dow Corning and GE, they take that element and run it through their reactors and turn it into silicones. Bathtub caulkings is what everybody comes to mind. Glues, It's used in dashboards, it's used in plastics, it's used in shaving cream, it's used in deodorants, it's used in cereal boxes, fake breasts, it's used in anything that has silicone in it starts out as that rock, as that element right there, element number 14. That's what comes out of the bottom of the furnace after it's tapped. The smoke, as you saw, used to go up the stack 50 years ago. Now they pull it down with fans and run it through a series of filters. After it comes out of the filters, it weighs what you have in that container. The densification silos that I talked about happen afterwards. But that's pretty much where it's produced. This is what it looks like coming out of the ladle. The hot silicon metal is poured into chills. That's exactly what it does in these big flat slabs, is chill. And then they drop it on the ground. It shatters like glass. That starts the crushing process. They crush it to that size, and they'll take it even further. They'll take it from that size all the way down to 10 micron in size, which is pretty damn fine. They use that in ceramics. This is actually, as you said, the silicon metal coming off, or the silicon. This is the silica fume, the silica fume going up the stack. As it comes off the silicon, it's all gas, SiO, gas. When it hits about 600C, it combines with another oxygen and forms an SiO2 solid. So you get this precipitation from a vapor to a solid, like a formation of a rain droplet. Is how the material ends up being so fine. Remember, we said it was 100 times finer than cement grains. It's captured smoke is what it comes down to. Yeah, that's a question that always comes up because of the name silica, and maybe these next couple slides show it better. This is another example of trying to give a perspective of what we're talking about here. If a cement grain, one little piece of powder of cement, were the size of the Washington Monument, silica fume would be the size of a 6-foot guy. That's the difference in size. On a typical mix, if you're using, and they normally use 5–10% silica fume cement replacement, if you're using that much, the calculated number is about 2 million pieces of silica fume for every cement grain, which I think is what it says down here. No, must be the next one. When this material is formed into a solid from this vapor, this is a real close-up of what the material looks like. Little glassy spheres. I had somebody look at this, some researcher looked at this, and they didn't know what it was. They were calling these, what did they call them? Oh, they call them Death Stars. Because of the, obviously the way it's formed. But because they're amorphous, amorphous means non-crystalline. And crystalline silica is what produces silicosis. Crystalline silica is what you'll find in the beach. The sand, the dust that's blowing off the beach, since you're getting ready for spring break here. Don't lay on the beach too much, you'll get silicosis. How's that? But that's crystalline silica. Crystalline silica, when you find powder, you'll breathe in, it'll get hung up in your aerosols in your lung sacs, and that's the start of silicosis. Where this material round is considered respirable, you breathe it in, you breathe it out, it doesn't get hung up in your lungs. It's one of the cleanest things in a ready mix yard, safest things. People don't think so because it has the name silica, but they keep thinking it's crystalline silica and it produces silicosis. You have to tell them all the time, you use silica in your plant, in your sands all the time. You put sands in your concrete all the time. Sand doesn't react with cement water, does it? You can cut open concrete 10 years later, look at it under a microscope, the sand's still there. You put silica fume in with cement, 7 days later, you cut it open, look at it under a microscope, you won't find any of the silica fume because it's reacted. Amorphous silica reacts, crystalline silica does not. Even though there's silica in the title, they're two separate materials. This is another shot of trying to show the particle packing theory. Dr. Hover on the video was talking about fitting in these little balls between other balls, and this is a shot of actually a cement grain. One cement grain here and one cement grain here, 1 micron scale, and that's silica fume particles mixed in within. I always use the example of if you can visualize filling up a barrel full of baseballs, you can only get those baseballs so close together, and you have void spaces between all the baseballs. Capillary pores in concrete, just like regular concrete. If you mix yes.
But just in a relative scale, how big would like a water molecule will be, or the chloride molecule be fit in between there?
In the chloride's case, it's in a dissolved state in water. And really you're talking about,
I guess what I'm really asking, would there still be some penetration?
yeah,
But not as much.
right, right. Because you've put something between those spaceballs. Otherwise, you know, you could pour water through it pretty easily, just physically blocking the pores. That's what the ceramic people do in their particle packing theory. Their theory is if they get all the particles graded just so that if you squeeze them all together, there's no room. It's 100% dense. That's why you get some little ceramic parts you put in your hand. They're this size and they weigh 3 pounds. You know, they're just so densely packed together of particles. And that's what we're trying to do with concrete. If you think about it, that's what we do on the aggregate side. We start off with big aggregate, we mix in a gradation of aggregates and then a gradation of sand so that when you put all those things together, they fit together very nicely so that you can use very little cement, very little glue. So all we're doing now, instead of grading the aggregate, we're grading the powders. We're grading the mortars. We're finding something to fit in that finest fraction between the cement grains. But you still will have some permeability, yes, yes. Yeah, it's not waterproofing. It's not waterproofing. Your example, you're still getting a little bit through. Less permeable, though, compared to if you did nothing. And what... What's the difference? No, the rock that you have, the silicon, the elemental silicon is just Si. The silica fume is SiO2 amorphous. So there's not, they're two different animals. They're two different animals. The silicon that you have there is, when it comes out of the furnace, is about 3/9 pure, 99.9% pure. If you want to make, silicon chips or photovoltaic cells or something like that, you've got to push it up to 5 or 6/9 pure. They'll take that rock and do further things to it to drive out more of the impurities so that they can make silicon chips and wafers and those type things. But it all starts out as that material. Yeah, all starts out as that material. The fume is the waste material. You know, that's the pollution that used to float in the atmosphere and people used to have to sweep off their steps. As they're saying here, that the common thought was before the use of pozzolanic materials for particle packing, that the best you could do was lower the water-cement ratio. Use the least amount of a lower water-cement ratio, you have lower permeable concrete. So that was always the trend, that if you wanted low permeable concrete, you made low water-cement ratio concrete. And what the next slide shows is that's not necessarily the case, or there is ways, it is the case. You do get a lower permeable concrete at a 3.5 is pretty low, but by adding a portion of silica fume or replacing the cement with even 7% silica fume, you can get somewhere around 60 to 80% reduction in permeability, even at a real low water cement ratio concrete. All those different values there, 120D, those are all different permeability tests that people run on concrete. And this is just a way of comparing all these different test methods, showing, they more or less show the same thing, the same type of trends. So it takes very little of this particle packing to get the biggest impact. As you see, you have a point of diminishing return here at about 7%. From here on out, as a cement replacement, you're only producing strength. If strength is your goal in a high-rise building, you may be up there at that dosage. If you're doing a parking garage or a bridge deck, you probably don't need strength. You're looking for this, though. You're looking for a reduction in permeability to keep the chlorides out. Or a loading dock or an industrial floor or a chemical plant or a sewage treatment plant or anywhere where you have an aggressive chemical that's going to get into the concrete, because all concrete is a sponge.
You're looking for durability.